Welcome to Lecture 10, Equivalent Force Systems and Simple Distributed Loads. In this lecture, we're going to look at the further simplification of a force and couple system and have an introduction to simple distributed loads. In the previous lecture, we established that a force and couple moment system can be reduced to an equivalent system that consists of a single resultant force, F sub r, acting at a specific point O, and a single resultant couple moment, M sub r. Now we're going to look at further simplification of that equivalent system to just one equivalent single resultant force in the cases where F sub r and M sub r are perpendicular to each other. The first case we're going to look at is where we have a concurrent force system. In a concurrent force system, the forces do not produce any moment about O, so the equivalent system can be represented by just the resultant of those forces, F sub r. So when we say concurrent, we mean that the lines of action of each of the forces in the system all intersect at a common point. So we don't need to move anything to that common point and bring along their associated couple moments with them. So the equivalent system is just the force resultant F sub r with no moment in the equivalent system. Now this is what we've been doing since lecture 2 in our 2D and 3D exercises where we have a force system and we're asked to determine a force resultant. All of those systems have been concurrent force systems. The second case where we can create an equivalent system that consists of a single resultant force is the coplanar force system. In a coplanar force system, all the forces lie in the same plane, and if all the forces lie in the same plane, then each of their moments about O and the resultant moment will be perpendicular to the plane containing them. So let's look at that here in figure A. So we're saying we have a coplanar force system. Now this is different from a concurrent force system in that now the lines of action, and I know I'm not doing a very good job of drawing a straight line here, but bear with me. The lines of action do not all intersect at a common point. So it's not a concurrent force system. So when we move our forces to some point of interest, there is no point of interest that all the forces lines of action pass through. So no matter where we move the forces, we're going to have some associated couple moments that have to come along with those forces when we move them. And since the forces are all in the same plane, any associated couple moments will be all perpendicular to that plane. In other words, in this example, the couple moments would either be coming out of the screen or going into the screen, perpendicular to the screen. So if we move those forces all to O and sum the forces vectorially to produce F sub r, there's some resultant moment that is perpendicular to F sub r, and then we can account for that moment by moving F sub r away from O a distance d such that F sub r times d would produce m sub r. So now we have an equivalent system here in C that consists of just a single resultant force. The third case where we can create an equivalent system that consists of just a single force resultant and no resultant moment is the parallel force system. As the name implies, this is a system in which the lines of action of all of the forces are parallel to one another. So figure A here is an example of a parallel force system where all the forces are parallel to the z-axis, and when we move those forces to point O, all of their associated couple moments and the resultant moment produced by summing those couple moments will all be perpendicular to the z-axis. Now, similar to the coplanar force system, we can account for that resultant moment by moving F sub r in figure C here, the appropriate distance d, along a line that is perpendicular to the axis that m sub r was acting about, such that F sub r times d is equivalent to the resultant moment. Now let's look at simple distributed loads. Distributed loads are loads that act over an area rather than at a specific point. So remember that up to now we've assumed that all our forces or loads all acted at a specific point. Now in the example shown here, you can see a bundle of what looks like 2x4s, a real world situation, and the weight of that bundle does not act at a specific point. It acts over some area or specific length if we're looking at it in 2D. And it's hard to see here, but they're showing the loading as a constant loading over the width of the bundle of 2x4s. And this W is we're going to use that for our loading intensity. And the units on that we're going to see are pounds per foot or newtons per meter. The distributed loading that we'll be working with in this course can be represented as varying only along a single axis, and in our case that's usually going to be the x-axis, if not always. And in such cases, the loading W, the loading function, is going to be expressed as a function of x, and as we mentioned on the previous slide, that loading function is going to have units of force per length. We'll deal with problems involving distributed loading by replacing specific distributed loads with a resultant force F acting at a specific location along the length of the loading. So look at it, just a tip or a general distributed load here where the loading function is a function of x, and the area under the curve represents the total weight of the distributed load, which we're calling F sub r. And F sub r will act through the centroid, or the geometric center of the area. Now remember, our units on W are pounds per foot or newtons per meter. Our units on X are feet or meters. So the area under the curve is going to be pounds per foot times feet, which leaves me with pounds or weight. The good news is that for now, we're only going to consider rectangular and triangular loading diagrams, and which means we're not going to be doing integration to find the areas under the loading curves. So we'll be able to calculate the area of a rectangle easily, as well as the area of a triangle easily, which will give us the weights of that loading. And then the centroids of a rectangle and triangle are also very easy to determine. Let's look at a rectangular loading example. In rectangular loading, our loading function W is just a horizontal line. It doesn't vary with X, it's constant. And in this example, our loading is a constant 400 pounds per foot across the 10-foot length. Now remember that 400 pounds per foot represents the height of our rectangle, and the length that it's applied over is the 10 foot, which is the base of the rectangle. So our total weight, which we're going to call F sub r, is going to be equal to the area of the rectangle, which is just its base times its height. Base is 10 feet, height is 400 pounds per foot. When we do that math and consider the units, the feet cancel out, and we have a weight of 4,000 pounds. Now we need to find the centroid of the rectangle, and as we discussed on the previous slide, we will show that 4,000 pounds acting through the centroid. So the centroid of a rectangle is pretty simple. It's right in the center. We're only concerned with the X location of that rectangle, of the centroid, excuse me, of the rectangle, and we call that X location X bar. It's written as an X with a bar over it, and we read that as X bar. The Y location is known as Y bar, but we're only concerned with X bar. So should be obvious that we can calculate that location by dividing the base in half by 2. 10 feet over 2 gives us a centroid location of 5 feet. X bar is 5 feet. So we draw the equivalent system to this for the distributed loading situation as a force of 4,000 pounds acting through the centroid, which we said was at 5 feet from the left of the beam. Now let's look at a triangular loading example. In triangular loading, the loading curve is represented by the hypotenuse of a triangle, which means that the loading is varying in a linear fashion with respect to x. In this example, our loading function is 100x newtons per meter, which means that when x equals 0 at the start of the beam, at the start of the loading, our loading is 0, and when x equals 6, our loading tops out at 600 newtons per meter. Now remember that 600 newtons per meter is the height of that side of the triangle. So our total load that the beam is exposed to is the area of the triangle, and we're going to call that total load, or the total weight, we're going to call that F sub r again. The area of a triangle is 1/2 base times height. So we plug in those values, 6 meters for the base, 600 newtons per meter for the height. The meters cancel out, and we get a total weight of 1,800 newtons. So F sub r that we're going to put into our equivalent system is 1,800 newtons. And we're going to put that through the centroid of the triangle. And again, we only care about the x location, or x bar, of that centroid. And we can look up the formula for the centroid of a triangle, and we'll find that the location of x bar is 1/3 of the base, but starting from the right angle side of the triangle, or the heavy side, if you will, since this triangle is representing a weight. So this distance is the base over 3, but we need to reference things. In general, we'll be working from left to right on beam type problems. So this is x equals 0 over here. So we need this distance, and we show that down here for x bar. That distance, the x location of the centroid, is going to be the total length of the base of the triangle minus b over 3, and that's going to give us what's left there, and that will be 6 meters minus the base over 3, which is 2 meters, which gives us 4 meters. And so we show that there. And this is just should be intuitive. If it was rectangular loading, the location of F sub r would be farther to the left, but now more of the weight in the triangular loading is towards the other end of the beam, and so we show it makes sense that F sub r has to be somewhere past the midpoint of the beam as a result of the triangle being heavier, more weight towards the right end of the beam.